Okay, so first let's look at our JV curve in forward bias. So for the ideal diode, with our minimum J naught possible, we have JV equals J naught ideal times exponential to the voltage over V thermal minus 1. So the first thing we want to look at is, can we get rid of this minus 1? And the answer is yes. As long as V is a few times bigger than V thermal, then this exponential is going to dominate over this. So if V thermal at room temperature is 26 millivolts, that means every time we go above 26 millivolts, we're fine, we're safe. And then we can rewrite this as JV approximately J naught ideal exponential to the V over V thermal, as long as we're in a reasonable forward bias. Now, similarly, we could do the same approximations for the currents arising from recombination, and we would get J naught recombination generation, or otherwise known as Shockley-Reed-Hall, inside the depletion width times exponential to the V over V thermal, but we have to multiply by 2 for this mechanism here. Similarly, for high injection, we should get a 2 in the denominator. So our total current for a non-ideal diode, whether that non-ideality comes from it being a short diode or recombination generation in the depletion width, is going to be of the form J equals some J naught effective exponential to the V over neta V thermal, where neta is our ideality factor, and it's always going to be greater than 1. So equals 1 for ideal and greater than 1 for non-ideal. So because the current is approximately exponential as a function of voltage, if we replot the forward bias current on a logarithmic y-axis, we get some behavior that looks sort of like this. Now we can take slopes at the different regions, and it turns out for small forward biases, we're dominated by the J naught recombination. And in fact, we can read off that, that J naught from the intercept of this tangent line with the axis. Similarly, we can read off the ideal diode behavior from a slightly larger voltage range. But then at even higher bias, we end up back in a regime of ideality factor greater than 2, which would be high injection. And again, these slopes are going to be 1/2 times V thermal here, and V thermal here, and again 1/2 here. So we have 3 regimes of behavior all in forward bias here, dominated by recombination at rather low voltage, moving into a region of ideal behavior, and then finally saturating a bit in the regime of high injection. By plotting the diode current on a logarithmic scale And looking at the slopes of different regions, you can actually diagnose issues with diodes. For example, if you see a half-slope region at low bias, it indicates that there might be recombination centers present in your depletion width. So let's also now take a look at what happens into reverse bias. And then we'll wrap up by putting it all together. So on a linear scale, the ideal diode saturation current should saturate, and we end up with J naught at large reverse bias. Now, of course, we looked last time at what happens in breakdown, but we're not considering that yet. We're still saying that breakdown happens somewhere further out here. Let's look at what this all looks like on the logarithmic scale. So I'm going to redraw this. And because you can't take a logarithm of a negative number, what we're going to plot here is log of absolute value of j as a function of v. So we can look at the above graph and see that we should get some regions that sort of look like this. And in reverse bias, we should get, for an ideal diode, something that saturates like this. And if we have some non-idealities, such as the recombination mechanism, it might still continue to increase. So by taking all the data in forward and reverse bias, putting it on one logarithmic curve, you can start to diagnose a lot of things about the quality of your diode. So you might see either leakage or recombination currents in the depletion width and the reverse bias, and then you might see these three regimes of slope in the forward bias range. So RG ideal, and then high injection. You may also see parasitic effects. So if your diode has other non-idealities not having to do with the p-n junction itself, you might be able to represent your system, your total diode, as an equivalent circuit that has shunt and series resistance in it. So we could call this our shunt, and we're going to apply the voltage here. Our shunt, here's our diode, and then this is our series. And we put a black box around this, so to the outside world, this circuit is what we're seeing. The effect of our shunts will change the slope near the origin here. The effect of our series will be to sort of choke the current at high biases. So high injection and also our shunt can sort of look the same, except that what you'll see is a linear behavior in the roll-off for RS, whereas you'll see an exponential behavior still for high injection. So on a logarithmic scale, the high injection looks like a straight line, whereas the linear increase will present as a roll-off on the log scale. So I've tried to motivate a little taste of how you can use such graphs to actually diagnose problems in diodes after doing all the derivations of different non-idealities that can be present. So this concludes this section on non-ideal diodes. And now we'll move on to using the diodes in circuits and how they behave in the so-called small signal regime.